we talk about gases, we need a way to relate pressure, volume, and temperature together. Many of you have probably used this already, the ideal gas law. This is basically energy. P is pressure. Remember, pressure is pascals, which is newtons over meter squared. Capital V is volume. That's meters cubed. Meter squared cancels out with two of these. This term has units of newtons times meter. That is energy. So we're talking about the energy our gas has. N is still the number of moles. T is temperature, and it must be in Kelvin. Absolutely no exceptions to that rule. So if you ever use the ideal gas law and you are plugging in a value for temperature, your temperature must be in Kelvin prior to plugging it in. R is a constant. It's called the universal gas constant. With the units we're using, it has a value of 8.31. The units are, let's see, joules per mole Kelvin. And technically it is accurate to more decimal places, but our book has used just 3 significant figures of it. There are different R values depending upon what units you use for pressure and volume. For example, if you use pressure in ATMs and volume in liters, you'd have a different R value that would work as well. I can't remember what it is, because we always use newtons and meters. So, ideal gas law can be written one other way. Remember, the number of moles is the same thing as the number of molecules over Avogadro's number. So we can write the ideal gas law in terms of number of molecules as well. This quantity, R is a constant and Avogadro's number is a constant. This ratio of R over Avogadro's number we call the Boltzmann constant. R over Na, I can't remember what it is. 1.38 times 10 to the negative 23rd. And it has units of joules per Kelvin. So basically 2 ways to write the ideal gas law. One in terms of moles, one in terms of molecules. Which one do you use? Whichever one. If you know the number of molecules, use this one. If you know the number of moles, use that one. Or if you're looking for the number of molecules, use this one. If you're looking for the number of moles, use that one. Now the ideal gas law is just that. It's for ideal gases. The ideal gas law works as long as the pressure doesn't get too big, and as long as the temperature, basically the pressure and temperature don't get to a point where you start changing the phase, where you're anywhere near changing the phase of the gas. So as long as you are well within the gas region of your pressure temperature diagram, the ideal gas law will work just fine. As we talk about gases and the energy exchange, as we do things to our gases, we're going to talk about 4 different types of processes.
It was at a negative 0.3.
Yes.
10 to the negative 23 Boltzmann.
Yep. Okay, these are in no special order. One type of process we're going to talk about is isobaric. Iso, the prefix iso means same. Baric relates to pressure. So an isobaric process is one in which the pressure remains the same the whole time. So pressure is constant. That means if you change the volume, what else has to change? The temperature. Exactly right. Now I'm assuming we're maintaining the number of moles. So I'm assuming we have a container where we're not letting more gas in and we're not letting gas escape. If we change volume, temperature must change as well. So we actually end up with a really nice little relationship. I'm going to rewrite the ideal gas law so I have all the constants on one side and everything that's changing on the other side. So pressure staying constant, the N and the R are staying constant. The temperature and the volume are changing. But by writing it this way, if pressure is staying constant, N is staying constant, and R is staying constant, this whole term has to stay constant. So the ratio of temperature to volume has to be constant. You also can flip it over. Ratio of volume over temperature has to be constant. That's an interesting relationship we end up with for isobaric processes. What that means is the temperature at any one point in time over the volume of your gas at that same point in time has to equal the temperature over the volume at any second point in time during the process. When we talk about these processes, it's actually really common to draw what's called a PV diagram, meaning pressure versus volume. If pressure is constant, how can I draw something where pressure would look constant? What would it look like? Straight horizontal line. If I have some constant pressure, the pressure has to stay constant, so I'll have a nice straight horizontal line. So an isobaric process is always characterized by a straight horizontal line. Now, you can be going to the right or to the left, meaning your volume could be increasing, that would be going to the right, or you could have a similar process where you've decreased the volume, so that means you're going to the left. Another process we're going to look at is isocoric. In an isocoric process, volume is held constant. So you have a rigid container. The container cannot change size in any way. So that means if you change the pressure or temperature, the other will change as well. Pressure and temperature will both change. So if we do the same trick, if we write all of the constants in the ideal gas law on one side and all the things that are changing on the other side, this time volume is staying constant. That means the ratio of temperature over pressure has to remain constant. So if you triple the temperature, you'll triple the pressure as well. Okay? If we want to write it similar to that, we can have T1 over P1 equal T2 over P2. What would an isocoric process look like on a PV diagram? We're still graphing pressure versus volume. If volume's constant, we'll have to have a straight vertical line. Exactly right. Another type of process is an isothermal process. Temperature remains constant in an isothermal process. That means if you change pressure, volume will change accordingly. Conveniently, the ideal gas law for an isothermal process is already written with all the constants on one side. What this means is P times V has to stay constant. So pressure times volume will always stay constant. If pressure doubles, volume will be cut in half. So the 2 times 1/2 still gives us the 1, the original value. We can write this if we want as P1V1 times P2V2. This isothermal process looks like that. It's not exponential, but it looks kind of like an exponential function. Now, this is not a technical process, but it's on the test notes. What if you're not holding temperature constant, you're not holding volume constant, and you're not holding pressure constant? But all you're doing is you're making sure no gas is coming in or leaving. You'll have the same number of moles, and that's it. On the test notes, this is called iso stuff. That is in no way a technical term.
Is that like when it's in a balloon or something?
Yeah, exactly. So like a balloon where no gas can come into it or exit it. So what's staying constant is N. Now, in all of these, we've also implied the N stayed constant as well. In all of these relationships, we're assuming our container has no leaks, no openings, so no gas can escape and no gas can come in. Well, iso stuff, if we solve the ideal gas law with constants on one side and changes on the other, we're going to get PV over T. So that means P1 V1 over T1 is equal to P2 V2 over T2. On a PV diagram, it looks similar to the isothermal. This is just steeper. So it would go down to a lower value. A specific type of process that we're going to talk about that falls in this category is called an adiabatic process. An adiabatic process is one in which there's no energy exchange between the system and its surroundings due to temperature differences. So there's no significant difference between the temperature difference between the system and the surroundings. So we'll talk about the adiabatic process. So these equations here apply to adiabatic process. We're going to have some other equations as well that we'll introduce that applies to an adiabatic process.